Okay, so we hinted at it last hour. And this hour we're going to go into more detail, into variation. Variation is just the relationship between two numbers and how they change and how their change is related to each other. Most of the stuff we work with involves more than one value that work together, like our gear ratios and stuff like that. So variation is just a way of describing that and being able to work with it. Variation is one of the more powerful. It's part of ratio and proportion. I think ratio and proportion is probably the most useful part of mathematics because you can use it for just about anything. And variation is one of the more powerful sections within that because it allows you to take things that you don't necessarily have a formula for, but to figure out stuff without having to know that memorized formula or whatever. So the first type of variation we're going to talk about, as we mentioned before, is direct. In direct variation, if one number gets larger, the other number gets larger proportionally in a specified relationship. The general formula for direct variation is y equals a constant times x. So we use k just to represent that constant. Another way of expressing it might be that y over x equals a constant. And we mentioned we use that term last hour of a constant ratio. And that's what this is saying. The ratio between y and x is a constant. If y doubles, x has to double. If y is cut to a third, x is cut to a third. Because their ratio has to stay the same. So let's say we are told y varies directly with x. What that is telling us is the relationship between x and y is just this one right here. Y equals constant times x. Let's say the next part of the problem says y is 27 when x is 9. So what this is telling us now, this is what we would call an initial condition. So what we did up here is we identified what type of relationship we have. We know it's direct. We know as one gets bigger, the other one has to get bigger. Or the opposite. If one gets smaller, the other one has to get smaller. This is an initial condition giving us one set of numbers for those two variables within that condition. So that's saying y equals kx, y is 27, so I'm going to put 27 in where the y is when x is 9. So I leave the k, but I put 9 in where the x is. And now I can solve that by dividing by 9 to get that 3 equals k, or k equals 3. What that allows me to do now is to further define the relationship. Instead of y equals kx, y equals 3 times x is what that's telling us. So then the next step would be to go to a new condition where we might be asked, find the value of y when x is 7. Well, we know y equals 3x here. So I'm going to put 7 in for x. Y equals 3 times 7 is 21. So we found the value of y when x is 7. And we get into engineering work and a lot of other applied fields. It's a very handy tool to be able to do. Even though you may have forgotten the formula, you know that both numbers you have to get bigger together or they have that direct relationship. And so if you have an initial measurement, you know that so far what you've done every time x equals 9, y has to be 27 in this case. You can use that then to further determine the relationship. The only thing that's required here is a common 0 point. We talked about that in our measurement conversions as well. For measurement conversions to work, you have to have that common 0 point. 0 inches equals 0 centimeters, and so on. So then you can use that conversion factor to convert them. If we don't have a common 0 point, then we had to use that formula, which is a more complex way of converting. So let's do another couple of examples here. Y varies directly. There's a lot of different ways of wording this. Y varies directly with X, directly as X. Other ways of wording it as well. X and Y vary directly with each other. So Y varies directly as X. Y is 18 when X is 3. Find Y when X is 11. So again, Y varies directly with X. It's telling us the relationship. Y equals KX. Next, Y is 18 when X is 3. That's that initial condition. So what's going to go in for Y? Don't be shy. 18, right? Y is 18. Put in K here. What goes in for X? 3. X is 3. So 18 equals K times 3. What do we do there? Divide by 3 to get that 6 equals K. So that's telling us that this relationship here is actually Y equals 6X instead of just Y equals KX. Then finally, find Y when X is 11. So we put 11 in for the X. Y equals 6 times 11, or 66. What's that? Any questions? Not always quite that simple, but let's have you guys try one on your own. Y varies directly with X. Y is 36 when X is 9. Find Y when X is 7. So I'll give you a minute to do that one. So what'd you guys come up with for this? You know they're very directly, so Y equals KX. Y is 36 when X is 9. So what's K have to be? 4. So Y equals 4X. Put in 7 for X. Y equals 28. How many got 28? How about this one? Y varies directly as the square root of X. Y is 14 and X is 4. Find Y when X is 9. Tell me what to do here. Well, Y varies directly with the square root of X. That's a little different. Instead of Y equals KX, it's Y equals K times the square root of X. Then what's next? Apparently everybody took their Ritalin and done something. Everybody's out. So y is 14. Sorry, that was the right answer. Equals k times the square root of 4. So now we've got an extra step in here that we have to do. We have to actually do the square root of 4, which is 2. Then we can divide by 2. You get the 7 equals k. So y is equal to 7 times the square root of x. And then we put in here 7 times the square root of 9 to find y. So the square root of 9 is 3, so 7 times 3 is 21. Y is 21. Some examples of direct variation. We saw some examples in the last hour with the gear size and pulley size. If you know you need a certain gear ratio, what's it going to be? Well, let's say you have currently a motor with 9 teeth and, let's say we're running a conveyor with it. A conveyor with 21 teeth. Need to replace the motor the new motor has let's say the new motor has 15 teeth on it. How big of a sprocket do you need on the conveyor now? Well, we know it's direct. We know y equals kx. Where we're going to let k be the conveyor and x be the teeth on the motor. So our initial condition is the motor had 9 teeth, so that's x. The conveyor had 21. So divide by 9. That ends up being 7/3 equals k, or 2 1/3 if you want to simplify it down to a mixed number. I'm going to leave it as 7/3. So y equals 7/3 times x. So now if that motor has 15 teeth, it's 7/3 times 15, which is 35. We need 35 teeth in the gear on the conveyor to keep it at the same speed. Scale drawings. Any blueprints you're going to be asked to read. How many of you helped out with the skills thing with the high school kids last week? None of you guys did? Okay. That was probably the single biggest mistake anyone made. It wasn't the quality of their welds that was the issue. It was reading the blueprint and doing the correct thing that they were supposed to be doing. So if you have a dimension on there that is 3/4 of an inch on the drawing, that's the drawn dimension, which represents a real dimension of 6 inches, then something that is 1 1/4 inches on the drawing is going to be how long in real life? So the same thing. Y equals kx. You know that 6 inches equals k times 3/4 of an inch. Divide by 3/4. 8 equals k. So you know that y equals k, 8 times x. The real dimension equals 8 times the drawn dimension. In other words, it's a 1/8 scale. So y equals 8 times 1 1/4, which is going to be 10 inches. Not so bad? Okay. This just happens for maps and all sorts of other things as well. Now this is the case, by the way, generally I wouldn't do it out with variation here. This is one where I would probably set up like this. 3/4 of an inch equals 6 inches. Remember, we said one thing for direct variation. It's a constant proportion, constant ratio. 3/4 of an inch equals 6. 1 1/4 of an inch equals what? And cross, multiply and divide. 6 times 1 1/4 divided by 3/4 will give us 10 inches here. Let's say that you're looking at a medication and you need to take a painkiller and you're not sure how much to take. And you know that it's based off of weight. You have a friend who is at a weight of 120 pounds, was told to take 600 milligrams. Let's say you are a weight of 180 pounds. How many milligrams should you take? So again, we know that y equals k times x, where we are going to let y equal the medication in milligrams and x equal the weight in pounds. So we know that there was 600 milligrams prescribed to the person who weighed 120 pounds. So we divide that out. We divide by 120, and we get k equals 5. So that's telling us it's 5 milligrams per pound. So y equals 5 times x. And we say, okay, we are 180, so y equals 5 times 180, which equals 900 milligrams for you. Make sense? Mechanical advantage is another one. Let's say for a block and tackle system you've got set up, you need to, if you pull with 50 pounds, it will lift 450 pounds. Want to know how much force is required to lift 800 pounds. So let's look at this. Again, this is y equals kx. This is a direct relationship. And if it takes, if you can lift 450 pounds, well, that be y is the amount you can lift with what you pull. You're pulling with 50 pounds. You divide this out. Nine equals k. Well, that's your mechanical advantage, is 9. You are lifting 9 times more than the force you're putting into it. Anybody know what the trade-off usually is for that? If you can lift 9 times more than the force you put into it, 9 times the distance, yes. If you need to lift it 2 feet, you've got to pull the rope 18 feet to make it move that far. Actually, a little bit more usually because of friction within the system. So to get a true 9 mechanical advantage is actually more than a lot larger than a 9 theoretical advantage. So how much force does it take to lift something that is 800 pounds? 800 go in for x or y? That's how much you're trying to lift. That goes in for y. So we have to divide out the 9, which is going to give us what? 88.9 pounds of force is what it would take to lift that. Okay, so the other type of relationship that we mentioned briefly is something called an inverse relationship. In an inverse relationship, when one number gets larger, the other number has to get smaller in a related manner. For example, if one number doubles, the other number has to get cut in half. One number triples, the other one gets cut to a third, and so on. Our basic formula for an inverse relationship is y equals to a constant divided by x. And we mentioned this earlier as well. It's a constant product. So that means x times y is a constant. Two of them multiplied together. We can use them in this form a little bit, but generally we'll use them like this. Now I'm not going to go step by step to start off here like I did with the direct, because we've seen direct now. We can move a little faster. So let's say we're told y varies directly, y varies inversely as x, and y is 8 when x is 6. What is this telling us? Well, y varies inversely as x is telling us y equals k over x. This here then is our initial condition. It's giving us a starting point. Y is 8 when x is 6. And we can solve by multiplying by 6 to get 48 equals k. So that's telling us the relationship here is y equals 48 divided by x. Now I didn't give you a second condition there, but we'll do that in this next problem. Let's say y varies inversely with x. Y is 8 when x is 9. Find y when x is 6. So again, y varies inversely with x is just y equals the constant divided by x. Y is 8 when x is 9. So 8 goes in for y, 9 in for x. What's k going to end up being? Multiply by 9 to get rid of it. 72 equals k. So y equals 72 divided by x. And then find y when x is 6. So 72 divided by 6 is 12. So another one for you guys to try. Y varies inversely with x. Y is 6 when x is 8. Find y when x is 3. Try that one in your notes quick. So y varies inversely with x. Y is 6 when x is 8 gives us 48 equals k. So y equals 48 over x. So when x is 3, what's y have to be? 16. Good. How about this one? Y varies inversely with the square of x. Y is 48 when x is 2. Find y when x is 4. So the relationship here is a little bit different. Y varies inversely with the square of x. It's still y equals k over, but instead of x, it is x squared. So y is 48 when x is 2. We put 2 in, so it's 2 squared down there by the x. 2 squared is 4, so 48 equals k divided by 4. And to solve for k, we multiply by 4. So 192 equals k. So y equals 192 divided by x squared. Find y when x is 4. So 192 over 4 squared, which is 192 over 16, which is 12. Y is 12. Some examples of inverse variation. One is the gears and RPMs we've been talking about. Pretend these look right. So here we've got a gear with 8 teeth and one with 12 teeth. If this gear here is turning at 720 RPM, what's this one turning at? Well, we know it is an inverse relationship. Y, which is the RPM, it varies inversely with x, where x is the number of teeth. So we know that 720 RPM, oops, it should be inversely, shouldn't it? So it should be k over x, where x is the number of teeth. So 720 equals k over 8. We multiply by 8 here to get that k equals 5,760. So that tells me that y equals 5,760 divided by the number of teeth, divided by x. So here, 5,760 divided by 12, 480 RPM for the bigger gear. Now again, just like we did with proportions, we can set this up as a constant product. We can say that for gear 1, we have the RPMs, 720, times the number of teeth. And that has to equal the RPM for gear 2 times its teeth, which is 12. So you multiply this to get the 5760, and then divide by 12. Gives you the 480 RPM. Another example is a lever. For a lever, the closer you are, well, the further you are away from what you're lifting, the less force it takes to lift it. So let's say that you are lifting a rock. Here's your fulcrum of your lever. And let's say here it takes, say, 50 pounds of force to lift that rock when the handle here is 40 inches long. Let's say you increase that handle. This length here doesn't change, and the size of the object we're lifting doesn't change. Let's say you put a longer handle on. This handle is now, let's put it at 60. Okay, that won't work out very pretty, but we'll give it a shot. 60 inches. So again, we know force is equal to a constant divided by your distance. So your force of 50 pounds equals a constant divided by 40. Multiplying by 40 gives you 2,000 equals your constant here. So that's telling us our force is equal to 2,000 divided by our distance. So when we change that to 60, 2,000 divided by 60 gives us 33.33 pounds. It's reduced to 33 1/3 pounds. It'll be reduced to. Your ideal gas loss is the same thing. Your pressure and your volume, as long as your temperature doesn't change, pressure and volume are inversely related. So let's say that at 30 pounds per square inch psi pressure, the volume is 72 cubic inches. Find the volume at 50 psi. So again, the volume is inversely related to pressure. V equals K over P. We know that it is a volume of 72 at a pressure of 30. So multiply by 30 to get K. This is what? 2,160 equals K. So we know that the volume is 2,160 divided by the pressure. So we put in that pressure of 50 psi, which is going to give us, what, 43 points. Not 43, 41. No, 43. That can be decisive, huh? 43.2 is that'll be cubic inches. It's going to be the volume. What do you think? There's a lot of stuff that variation applies to. Now let's take a look at a little bit more complicated system here. Pulleys. So we have here a 4-inch pulley that is turning at 1,200 RPM. And it is turning a, let's say it is turning a 16-inch pulley here. Attached to the side of that 16-inch pulley is a 3-inch pulley that is going to a 6-inch pulley. I want to know how fast. What's the RPM of that 6-inch pulley? So I start out here. First relationship, 4-inch pulley turning at 1,200 RPM. So 1,200 equals K divided by 4. Oops, not divided by 4. Actually, that is true. K divided by 4, right? Because inverse relationship between the size and the RPM. So we multiply by 4 there. 4,800 equals K. So jumping to this next pulley, the RPM, this pulley here, the RPM is equal to 4,800 divided by what? 16. We divide that out, we're going to get 300. This is the RPM. How do we find the RPM for this 3-inch pulley? Trick question. It's 300. Why? Because they're attached. So now we have a new situation here. It's 300 RPM on a 3-inch pulley. So 300 equals K over 3. Multiply by 3, you get 900 equals K for this set. So this belt, the pulleys on that belt have a constant of 900. So the RPM here equals 900 divided by the diameter. That one is 6, right? So 900 divided by 6, the RPM is 150 RPM for that last pull. Any questions? Okay. In your book, page 294, exercise 7.3, 1 through 53 the odds, goes over direct variation. On page 297, exercise 7.4, 1 through 43 the odds, goes over inverse variation.